possible flow, and that in 1 decade, sorry, 2 decades, you would reach 90%.
That's
right. No. Oh yes, you're right. You're actually right.
Can people on Zoom hear me?
The omega is this way. So like as the
Can people on Zoom hear me? Hello. Test. Anyone on Zoom? Am I muted? No, I'm not muted. Okay, great.
But it kind of makes sense. I just we didn't have the not just as big as that. We had a well, we didn't learn a second. You should have well, I think that's yeah, that's what I mean. That while we're trying to look at that, we're given. This should be like really look about that is that yeah.
All right.
Definitely has to be right. Yeah, we're talking about like a thing that I charge you and you know that I have to like yeah. They want to do their problems. That's the thing. That's the way to solve
All right. Good afternoon. How's everyone doing? We released the midterm grades. How do people feel about that? Good, bad? Yeah, fair enough. Yeah. The exam was a bit harder than what we were expecting. We are going to reduce the maximum score a bit. Uh, we'll see how things go once we finish up regrades. We should be opening soon, I think, right? If you go onto Ed, you can check when they'll open up. Uh, did anyone have any questions about the midterm before we start today's material? We don't really have much going on right now. It's just start to work on project 3. Get partners. Just show of hands. Does anyone here not have a partner right now? All right. Uh, those are people who do not have a partner. Hint. And they are apparently free during the Monday, Wednesday, Friday slot from 1 to 2. Most likely. So, all right. Let's get started today. So we covered Mergesort a bit briefly in an earlier lecture. I think we covered it slightly during the asymptotics lecture. Let's kind of go over what it is fully. So we discussed how selection sort works. We take an item, or we take a list, we look for the smallest item, we move it to the front, and then we just repeat over and over on each sublist. The runtime for this was theta n squared, because it takes a lot of time to find the smallest item in each set. It takes n units of time to find the smallest, and then you got to look at n-1, then n-2, then n-3, and so on. Eventually, you look at one item. The total runtime is theta n squared. So if you consider the runtime as quadratic, for n equals 64, we can say the runtime is just about 4096. That's 64 squared units of time. It doesn't matter the exact value. It's just an approximation. It's a good way to sense like about how much time it'll take. So one thing we were able to find was that if we had 2 already sorted lists, it's actually fairly quick to combine the 2 lists together. As an example here, if we had these 2 lists, we can combine them by just looking at these smallest items and moving them in one at a time. So 2, 3, 4, 5, 6, 7, 8. Using this, we're able to get a merge done in theta n time. So here we talked about how the merge would run in total theta n time. Because if you look at it overall, we look at each individual memory address exactly once each. So it takes n units of time because there are n total items. So one approach we could do is we could just take the left half of the array, selection sort it, take the right half of the array, selection sort it, and then merge the results in theta n time. And if you look at how that ends up working, this n equals 32. You square that value, you get 1024. You get a square on this side, that's 1024 on this side. And then you take 64 units of time to combine these up here. You end up overall at 2,112 units. That's just about 2,048. Which is much better than the 4,096 that we had originally. So if we were to keep doing this layer by layer, we'd eventually manage to reduce the time even further. We can split 1,024 units of work into 2 256s plus the 32. And if we just keep going all the way down, we end up at kind of our idea of merge sort. We recursively split into half. We merge sort the left half, merge sort the right half, and then we merge the results in theta n time. If we were to do that, how much time does this take? Constant? Well, what's the total runtime of the merge sort algorithm, I should say? Yeah, n log n. The exact reason why is because each of these layers takes 64 units of work to complete. And then we just keep going down where k is the number of layers. And how many layers do we have? Log n. Why is that?
Like
Yeah, it's kind of like a tree. If we want to increase the height by 1, then we need to double the size of our initial list. So we have a log base 2 n here. So what's the total worst case runtime? Everyone say it. N log n. Yes. The exact count is complicated. It's omitted here. You can see, I think we have an optional textbook that shows exactly how it works. So overall, the time complexity is going to be n log n. What about the space complexity? How much space does this take? Anyone have a suggestion? How much memory does this take?
Yeah.
Huh?
When you have like a recursive stack of size log n, so it's at least log n.
Yes, you do have a recursive stack of size log n, so it at least has log n memory. Any other pieces of memory we are using here?
Probably same.
Yep. We have theta n units of memory to spend on these arrays. When we're splitting into two halves and merging them together, we kind of need to create a separate array to store the merged data together. And that's going to take an extra theta n time, or theta n memory, sorry. Now, it is possible to do an in-place merge sort, which gets rid of the auxiliary array cost, so it goes back to your log n. But the algorithm is really complicated. The runtime ends up suffering by a really large constant factor. It's generally not worth it to do that. So let's kind of look briefly at how merge sort would actually work on a list. So we'll split each the array down into two about even pieces. We'll merge sort each half, and then we'll merge the sorted halves together to form our final result. So here, I'm splitting them into two roughly equal halves. I'm just arbitrarily picking the right side to have one more item. It doesn't matter really which side it goes. We'll merge sort each half. This is not shown here. It is a recursive algorithm, but in effect, we just split it up and just recursively solve each sort. And then we'll merge the two halves. So we'll put in an auxiliary array here, and we'll just merge them together. So how do we merge them? What's the first thing that gets moved? 2. Yep. We'll compare these two smallest items, and we'll put the 2 in. Then what? 15. Then 17. Does it matter which one we put in? Not really. I'm just going to arbitrarily pick the right side. Then 17, 17, 19, 26, 32, and then 41. Now this side ran out of items, so we just copy over the rest of these items in. That's just a minor edge case here. But overall, we end up getting this list, which is the full merged sorted array. So overall, we end up with a merge sort that's theta n log n. Best case runtime is also n log n because you still need to do all these merges. It does take theta n space, so it is less space efficient than heap sort. But if you look at the actual runtimes and try running this on an actual computer, you'll see that merge sort is actually quite a bit faster than heap sort. The reason why isn't covered really in this class. Once you get into 61C, you'll talk about caching, which explains how certain memory operations are on the order of 1,000 times faster than certain other memory operations. It just so happens that merge sort uses a lot of those fast memory operations, while heap sort uses a lot of those slow memory operations. So while it's not asymptotically better, merge sort is going to end up being practically better when running things. All right, any questions about merge sort? Yeah.
When you're doing this space complexity, was it n plus log n time?
With space complexity, it would be n plus log n. Kind of the reason why is that once you use one of the auxiliary arrays, we can just kind of save it onto the into the old space within the array. Another thing to point out is that the value of n halves at each step, right? So the total memory used in the worst case is n units for the top layer plus n over 2 for the second layer plus n over 4 for the third, and so on. And that just adds up to n because it's a geometric sequence. Yeah. All right. Let's move on to another sort. So let's see how far we can get. Today we might just go over the insertion sorts and a few miscellaneous sorts. Well, let's see if we have time for quicksort. But first we'll go over some actually bad sorts that don't necessarily have too much use directly. But we'll see how they might be useful in some contexts. So here's another sorting algorithm. And the idea is like this. We start off with just an empty output sequence. And what we'll do is we'll add each item from the input, storing it in the right spot that it goes. So the output will always be sorted, and we'll just be inserting new items into our sorted list one at a time. You can imagine this is kind of something you might do in real life. If you have a lot of things to sort, you just take an item, you put it in line. You take a new item, you put it in its right spot relative to it, and then you keep doing that. If you have, let's say, a bookshelf with, let's say, 10 books on it, you might sort it in that way. So let's try doing it this way. So first off, I'm going to put the 32 in my input. Where does it go? Just in the list. It doesn't matter because there's like no list here. So now we look at 15. Where do we put it? Before the 32 or after the 32? Before the 32, yes. We now look at 2. Where do we put that? Before the 2, 15, yes. And then between the 2 and the 15, or sorry, between the 15 and 32, I am bad at insertion sorting. Between the 17 and 32, between the 19 and the 32, after the 32, next to the other 17, it doesn't matter where it is. I'm going to put it between the 17 and the 19. We'll explain why that is next time. And then 17? Yeah, between the 17 and the 19. So using this, we are able to get this in a sorted order. So what do you think is how do you think this runs? Well, for a naive approach, if the output sequence contains k items, the worst case cost to insert a single item is k units of time. Why is that? Huh?
Check with the output in element in the output array and potentially input in the last.
Well, you do have to check with the output array, but you could theoretically do this in log time if you do binary search to find where the spot is. Yeah, we still need to store this in an array somehow, and we are going to need to move each item one space to the right in order to insert it properly. You could make it easier to insert an item into a list using a linked list structure, and then maybe at the very end, like convert it back into array. But if you do that, then you can no longer do the log n binary search to find the right spot. So either way, it's going to take theta n time to complete an insertion step. A more efficient method, instead of doing this, would be to do some in-place operations. You kind of sort things by swapping items in place. Here's kind of a look at how it works. We'll use one color to denote the sorted portion and one color to denote the unsorted portion. And we'll look at how an item moves through this list. So first off, we'll just stay with 32. 32 is the first item, and we'll move it to its right spot in the sorted portion. There's no sorted portion yet, so it just stays there. It doesn't move. So now we have a sorted portion and an unsorted portion of our list. We'll look at this, 15, and we'll look, where should it go? We'll compare it to the next item. Should 15 swap with 32? Yes, because 15 is less than 32. So we swap it. We'll just keep swapping backwards until the traveler is in the right spot. In this case, is 15 in the right spot right now? Yeah, it's the smallest item in its list. There's nothing else to move. So it stays there, and now it's in the sorted spot. Now we look at 2. We compare to 32. Should it swap? Yes. What about now? swap. And after we finish swapping, this portion is sorted again. And it's kind of similar to that old insertion sort idea where we have each item move to its right spot. 17, swap. Swap or no swap? No swap. So now we add a new item to the sorted portion. The 19, swap. 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 No swap. 26, swap. No swap. 41, everyone, no swap. 17, swap. 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 No swap. And then the 17, swap, 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 no swap. And using this, we are able to get our array sorted. So what do you think the runtime is for this? N squared? Why?
Would be totally descending order. So you'd have to swap every element.
Yeah. In the worst case, you're swapping every other element back if you have a descending order. Here's kind of an example of like how potato might work. If you're trying to swap the letters in potato, you might have all of these. You'll have a total of 7 swaps here. And you can kind of see that these items that are really far away from where they end up needing to go end up moving a long distance and cause a lot of swaps. Here's another example. If you have sort example, you end up getting this triangle of swaps, which is kind of a lot of them. In general, what do you think the runtime is going to be? Let's discuss with your neighbor for about a minute. All right, let's bring everyone back. So first off, what do you think the O bound is? How many people say it's O of n runtime? How many people say it's O of n squared? Why is it O of n squared? Yeah. You see this triangle here that grows at a size of n squared. In the worst case, like you might be moving every single item all the way to the left, so the entire triangle gets filled. What's the best case? How many people say it's omega 1? Omega n? Omega n squared? Why do people say it's omega n? Yeah, if it's already sorted, you just look through each item in the list once. You don't cause any swaps. Yeah. Now, technically, you can say omega 1 because omega is just a lower bound and 1 is a lower bound, but it's not the best statement you can make here. So overall, insertion sort does seem like it does well. In some cases, it does omega n, but it could, in the worst case, take n squared time. So sometimes, depending on the items you might be working with, you might prefer different algorithms. So let's say that we have this exercise. We take 1,000,000 integers from a file. We merge sort these items, and then we'll just pick a random item to change it. And then we'll sort the algorithm using whatever, or we'll sort it using whatever algorithm you pick. Which sorting algorithm do you think would be the best choice in this case? Feel free to discuss with your neighbor. Let's take a minute on this. All right, let's bring everyone back. All right, which sorting algorithm do you want to use? How many people want to use selection sort? Few people. Heap sort? Merge sort? Insertion sort. Everyone wants to use insertion sort. Why? It's n squared. Isn't n log n better than n squared? Yeah.
Well, we know that everything except for like one number is already in the right place. And we said that if it's a sorted array, then it's omega n. So since there's only one item out of place, it's going to be a lot closer to the omega n than O of n.
Yep, that's a good argument. Let's try actually formalizing this. So in effect, what was said was since there's only one item out of place and the items that are in place, they don't end up moving at all. So they end up going fast. You should end up getting close to the omega n side, theta n side, than the n squared side. And that's true. Let's actually show why this is true. So recall what we said earlier, that we define an inversion as a pair of elements that are out of order. So for example, this 26 and 17, this is an inversion because the 26 is in the wrong spot relative to the 17. Now there's 9 choose 2 total different pairs you could pick in this list of 9 items. So that's 45 inversions at most. Another way we can state the goal of a sorting algorithm is to get a sequence with Z inversions and reduce that number of inversions down to 0. So for example, this is 19 and 17, that's out of order. Here's a few other inversions. And then if we just count them all out, we see that there are 6 total inversions in this list. Now, one thing we can note is that when we swap items in insertion sort, it reduces the number of inversions by 1. Now, why is that true? Well, let's look at what happens in a swap. We're always swapping 2 items right next to each other. So if we look at these red items, if there are any inversions between 2 red items, does that change anything? No, they don't move. So if there was an inversion there earlier, there's still an inversion there now. We still haven't swapped their order. If we compare one of these red items to one of these 2 items that moved here, has that inversion been fixed? No. Why not? Because they're still the same relative sides of each other. Any items here, 2, 15, 17, 19, they were to the left of this 17 and 26, and they're still to the left of the 17 and 26. So any inversions that might have occurred there earlier, they're still stuck inverted. In fact, the only thing that could fix an inversion is this swap here, because those are the only 2 items that swap their relative order. because of that, that's the only inversion we could possibly fix. And in fact, every single time we do a swap, we are fixing one inversion because we say that we swap only when these items are out of order of each other. So we fix them by getting them in order of each other. What that means is if we have this list of 6 inversions, how many times are we going to swap with insertion sort? 6 times. We don't know exactly when they're going to happen, but we do know that we are going to swap a total of 6 times because each time we swap, we reduce the number of inversions by 1, and we have 6 inversions to get down to 0. That also means that if you have a list that has very few inversions, you're not going to have that many swaps. This left array here has 5 inversions total. This right array here has 3 inversions. So we'll only have 5 swaps and 3 swaps respectively. So if you have this list, how many inversions are we going to have in the worst case? Yeah?
I have a question. How are you determining the number of inversions?
How are we determining the number of inversions? Well, it's fairly tricky to do so in practice. Here we're just calculating them out by counting them. Just look at every single pair of items. There's n squared total pairs you could look at. And then that's the total number. Yeah. In practice, you never actually compute the total number of inversions because that just takes way longer than actually sorting the list. But when we're doing kind of the theory behind things, we can do that to show what's happening.
You did something like 9 choose 2.
Yeah.
How do you get 45 and how is that?
So 9 choose 2 is just a quick way of saying the number of ways to choose 2 items out of a set of 9. You'll cover this more in CS70. But the idea is you pick one item to be your first item. You pick a second item to be your second. So that's 9 times 8 total possibilities. But if you pick A and then B, that's the same as if you picked B and then A. So you kind of divide by 2 to account for the fact that you overcounted by a factor of 2. 9 times 8 divided by 2? Yeah, that is 36, isn't it? Darn. I did 10 choose 2 here. Sorry. My math is bad. Good point. Yeah. 9 choose 2 is 36, not 45. Yeah. Good point. Either way, it is still n squared because it's still n times n minus 1 over 2. Yeah. So it is still going to be theta n squared in the worst case, maximum number of inversions. Anyway, in this list where we have everything sorted, but we changed one item, how many inversions can we have at most? Yeah. Yeah, O then. Why is that?
The least element or the greatest element could be on the opposite side.
Yeah, we could change the smallest item to be larger than everything else, and now we have 1,000,000 inversions. We can't have any more because you can only have inversions between the item you changed and every other item. So overall, if we have theta n inversions, what is our runtime for the insertion sort? Theta n, because we do exactly one swap for every inversion. In particular, we're going to have n plus k, where k is the number of inversions, which for a random list does end up being close to theta n squared. You can show that mathematically. Each inversion has about a 1 in 2 chance of existing, right? If you have 2 random items that are in random positions, they're either one greater than the other or one less than the other. On average, half of them are going to be inversions. And if you have n squared total inversions, you have n squared over 2 total inversions on average. Sorry, if you have n squared possible inversions and half of them are true inversions, then the number of true inversions is half of n squared or n squared over 2. So if you have an almost sorted array, though, which has about n inversions, then insertion sort is actually going to be really fast. It's going to be able to run really quickly because the number of inversions are so low. Now, a less obvious fact is that insertion sort is actually really fast for small arrays. Now, this is not really something you can prove mathematically. It's just something that we found when we try running this on an actual computer. Kind of the reason why is because creating new arrays, like you do with Mergesort, that takes a lot of time. And while it's not an asymptotically a significant amount of time, it is a practically significant amount of time. Insertion sort is all in place and it only moves things right next to each other. So for really small sizes, the constant factor is much smaller. And because the constant factor is smaller, constant factor times n squared is going to be smaller than a large factor times n log n for sufficiently small values of n. So in practice, what actually ends up happening in a real implementation of merge sort is that you merge sort not down all the way to small single element lists, but you merge sort down to size 15 or 16 or so, and then you just insertion sort at that smaller level. Using that, you get kind of the best of both worlds. You get the n log n runtime of merge sort, but you get the really fast runtime for small arrays of insertion sort. Any questions here? All right. So here are our sorts so far. We now have this in place insertion sort. It does take theta n in the best case. It is n squared in the worst case, so we generally don't want to use it for big arrays. But as it turns out, for small arrays or almost sorted arrays, it tends to be much better than merge sort. So we'll be using that for small arrays and switching to merge sort for big arrays. All right. Now, there are a ton of other sorting algorithms. Not all of them are actually practical, but they still get referenced every now and then. We haven't yet covered the fastest sorting algorithm. I'm going to save that one for last. But before we do, I want to go over a few fun algorithms that get covered a lot in these types of lectures, even if they're not actually practical. So one thing we need to note is that insertion sort is really good when the list is already sorted because it takes time proportional to the number of inversions. This is known as an adaptive sorting algorithm because it takes advantage of the order that already exists. It adapts to the sorting order because it already has some sort. Merge sort doesn't do this. You need to kind of resort the entire thing. So if you have an almost sorted array, it still takes as long to merge sort something as if you had a completely unsorted array. So sorting algorithms that are adaptive, they tend to work like this. They find a pair of adjacent elements that are in the wrong order. If you can't find any of those, then that means the list is fully sorted, so you're done. You'll swap those two items, and you just repeat this over and over until the list is sorted. Step 2 fixes one inversion each time, so you get theta k time from that step. Step 1 in insertion sort was really fast. You just look at each item, and the order in which we looked at the items guaranteed that if we find an inversion, then we can find it quickly. So overall, it would take theta n plus k. Here's an example of a sorting algorithm where step 1 is much slower, but we still kind of follow this path. It's called bubble sort. And the idea is instead of finding items that are in unsorted order, we just look at the items looking through each pair of items, pair by pair, over and over again until we find a path where there's no inversions. So here's kind of how it works. We'll look at this 32 and 15. Are they in the wrong order? Yes. So we swap them. Then we take a look at this 32 and 2. Are they in the wrong order? Yes. So we swap them. 32 and 17? Yep. 32 and 19? Yes. 32 and 26? 32 and 41? No. So we just leave those as is. Then we swap the 41 and 17. Yep. 41 and 17? Yes. And then we just keep doing this. We look at 15 and 2. Swap. No swap. No swap. No swap. No swap. 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 No swap. No. No. Oh. Yes. Yes. No. No. At this point, we still need to keep going. This is already sorted at this point, but we still need to run through this list one more time to just confirm that. So we just keep going. Sort. Sorry. Check, 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 check. No swap, no swap, no swap. Once we go through this entire list once and we have no swaps in a pass, then we know that the list is sorted. And then we're done. This is slow. Why is this slow? Anyone want to say why this is slow? Yeah, in the back. Yeah, we're rechecking things we've already checked. So while bubble sort is kind of the simple way to sort something, it's practically not that useful. In theory, it's very slow because it doesn't find the inversions as quickly. In practice, it's actually about 5 times slower than insertion sort. So we don't want to use this. The reason why is that moving things left takes a really long time. Because you have a single pass through. It moves a lot of things to the right really quickly, but it moves things to the left only one space at a time for each of these passes. So these turtles are really, really slow to move over, and it takes a long time to move them. We have some other variations of insertion sort. Cocktail shaker sort is kind of similar, where we do bubble sort going to the left to right, but then we go right to the left for the next pass, and then left to the right, and then right to the left. That gets rid of these turtles, but it's still quite a bit slower. The reason why it's called cocktail shaker sort is because you're kind of shaka on the list. Shell sort is actually a slightly improved version of this, where instead of moving things only one at a time, we move things a large distance first. That fixes a lot of inversions at a time initially. And depending on the jump length, you can actually get better asymptotic runtimes in insertion sort. I think the worst case for some shell sorts involve like theta of n to the 3/2 or n to the 4/3, depending on what sequence of jumps you take. Yes?
Wait, does insertion sort use a linked list?
Does insertion sort use a linked list? Not really. We can do this on an array, and an array will tend to be faster than the linked list because of some caching operations that we don't talk about in this class. Yeah. So
basically for shell sort.
square root decomposition, I'm not sure what you mean by that. Talk to me after class if you want to discuss further. Yeah. Now let's try a new problem. Let's talk about shuffling. So when we want to shuffle a list, the idea is we're given a list of items and a random number generator, and our goal is to return a random permutation of the list. Now, the random number generator is going to, the way that works, you give it a number between I and j, and it'll give you a random number between I and j. Now, your goal is to get an even distribution of the items and a fast runtime. Ideally, we want theta n runtime, and we want to guarantee that every single possible permutation is equally likely. So discuss with your neighbors. Let's take 2 or 3 minutes to try and come up with an algorithm that shuffles this list using only a random number generator.
I think it would be less random. I guess if you're good about it, I don't know how you guess. I don't have to know.
All right. Let's bring everyone back. What do people think? How can you shuffle a list of items? Anyone have an idea on how to shuffle something? You could interleave them. Yeah. One thing that I like to do when I try to solve a problem is I try to come up with a real world example. And if I have a deck of cards, the first thing that I'm going to do is I'm going to probably do a shuffle like this, right? You interleave them, and then you just combine them in words together. How fast do you think that's going to be to like run computationally? Probably takes about theta n time to do a single one of these shuffles. That would be my guess, at least. It really depends on how you're doing it. But it looks like what we do is we cut it into half and we kind of randomly pick one of these cards to move in. This feels kind of like a merge, but in reverse. So that's probably going to take about theta n time. The next question is, how many times do I need to do this kind of operation before the items are evenly distributed? It's a bit of a tricky question. I don't have the research behind it, but the problem is, regardless of how you do this, you're probably going to get slight spikes and non-spikes. Most likely, this top card is going to end up staying on top of this pile because it was so you don't move all the items too much. This top card is going to most likely stay here at the top, no matter how many times I sort this list this way. Right? I can do this a second time. And then the ace is still on top. Yeah. So anyone have any other strategies? Yeah.
You just like randomly swap elements of the array.
Randomly swap elements? Yeah, we could do that. Pick a random location, pick another random location, swap the two. On average, how many times do you think you need to do that in order to fully shuffle the array? Well, we need at least n units of time to touch each single item. In fact, in order to hit each item at least once, we will need, I believe, n log n units of time. And even then, it might not be fully sorted. So that's not as good as what we want. It is n log n on average. Any other approaches? One interesting thing is, yeah.
Like pick a number from like 0 to like the length on random and then move that to the front and then keep doing that and adding stuff to the front until like you've gone through everything.
Yeah, that's a good idea. So we take this list, we pick a random item, and we move that to the front of the list. We pick another random item, we move that to the next item, and so on and so forth. Eventually, we get a fully sorted list. It's kind of like I take this deck of cards, I pick a random item, I put it at the start. I take a random item, I put it next. And if I keep doing this randomly, then I'm going to fully shuffle this deck, right? It's not really fast for a human to do because this takes a long time to pick an item. But for a computer, it's going to be fast. So here's how we'll do it. I pick a random 7. I'll pick randomly 7, and I swap it with the 1. Then I pick 9, swap it, and I keep just doing this over and over until I get a fully randomized array. What's the runtime of this? Theta n, because we look at each item once. Does it evenly distribute the cards? Is every single option equally likely? Yeah, I would say it is because each item has an equal probability of being any card, right? This leftmost thing, it has an equal probability of it being anything because we picked a random item to be there. And after that, the rest of the items, we can recursively or inductively show that they are an equally distributed set as well. In fact, each permutation has exactly one way of being created. And the probability of that being created is this 1 over n times 1 over n minus 1, all the way times 1 over 1, which is equal to 1 over n factorial. So each way has an equal probability of being used. So this leads us to a really bad sort called BOGO sort. While the list is not sorted, shuffle the list, and then try again. Keep doing this until we get a sorted order. So let's just analyze this. What's the best case runtime for this algorithm? Theta 1, theta n. You still need to check if it's sorted. And it takes n units of time to do that. What's the worst case runtime for this? N times, well, technically infinite, because you might not get lucky. If you might have to keep shuffling over and over and over, and you just get unlucky. What about the average runtime? N factorial? Yeah, n times n factorial, actually, because you still need to check the list being sorted. But on average, you'll take n times n factorial iterations before we get to the sorted order. Is this a good sorting algorithm? No. It takes forever to run. So generally speaking, if you're trying to sort a list of cards, you do not shuffle it over and over until you get lucky. I will also say this is also not even the worst sorting algorithm. There are competitions where people try to find the worst possible sorting algorithm. And the worst sorting algorithms take theta of Ackermann time. So remember the inverse Ackermann where we said that in order to get a value of 5, you have 2 to the 2 to the 2 to the 2 repeated 16,384 times? Yeah, these are sorting algorithms that to sort a list of 5, it takes 2 to the 2 to the 2 to the 2 repeated 16,384 times to sort. People do this because they are sometimes bored and like to come up with really slow sorting algorithms.
Theoretically, there's a function that goes. I don't know why I got in book, right? I was very interested in classical function. That there was a function that I know my friends made that grows so fast that you have to use absolute infinity to describe its growth rate. That's how fast it works. It's a finite number, it does terminate, but it's so fast that it requires the usage of large polynomials or even absolute infinity to describe the function's like growth rate. Like to prove the function terminates, it requires like a massive polynomial.
Yeah.
And like it basically it determines like even for it to sort something, it takes time. Like to sort out like
Interesting. Yeah. So yeah, there are some really large growing functions that exist. I'm not sure what you mean by you need infinity to use to describe it, because I don't think that's ever possible if you have a finite growing function. But there are definitely really fast growing functions. Oh yeah, Graham's function is really slow growing, but there are things that make Graham's function look really fast by comparison. Ackermann is slower than Graham's function. And there are some functions like trees that show up in Ramsey theory that end up growing way, way faster. But anyway, that's the math aside. Let's finish up today's lecture by just going over a quick preview of the final sorting algorithm that we'll be discussing in this section. So far, here are the good sorts. I'm not including BOGO sort or bubble sort here because they are bad and you should never use them in practice. Here are kind of the core ideas for them. Selection sort was finding the smallest item. Merge sort was merging 2 items. Insertion sort was finding the item's correct spot. Quicksort's main idea is partitioning. This is invented by Sir Tony Hoare back when he was a novice programmer. What he was doing was he was working on this crude automated translation project, like taking this. The idea was you needed to look into this dictionary of English words, find the word, and just swap it back and forth. Now, if you were to do this in a modern system, it would be theta 1 time to look for each item because you just store everything in a hash map. But in the old days, the thing that needed to happen, it would actually take a long time to actually find it, because back in these days, memory was stored in a ticker tape, and it would actually take time to move the ticker tape back and forth to the right spot. Because of this, what you would need to do is you would need to look through the dictionary, and it takes a long time to move to the right spots. So what turns out to be better is that you sort this sentence first, and then you just look through the dictionary tape once. Instead of going back and forth to find the right item in your hash map, you just look through the items one at a time, and you can find the items that way. So in order to do that, you needed to figure out how to sort an array. This is back in the 60s, so Google did not exist. So Tony had to come up with a way to sort things. And what he did was this. The main idea is if I have a set of items, what I'm going to do is I'm just going to split them up into small items and big items. I don't know what I mean by small and big yet, but that's kind of what I'm going to want to do. So I'll first sort all the smaller items, then I'll sort all the big items, and then I'll put the sorted list together. Intuitively, imagine if I'm trying to sort everyone in here by height. I might say, I don't know. What is the height of the average person in this room? 5'6", let's say. So I'm going to say everyone who's 5'6" and shorter, move to this side. Everyone who's 5'7" and taller, move to this side. And then I'm going to sort you individually, and that way I get my fully sorted list. That's kind of the way that we might think about doing this. We'll call this a partition. We kind of split the big items and the small items, and we put the remaining items kind of in the middle if they're equal to 5'6". So partition of this array is kind of like this. We split this up into even size, and we have a pivot here. Intuitively, I don't really know what I consider to be a reasonable medium-sized person, so I'm just going to pick a random person in this room to say, you are the medium-sized person. You are the medium-sized person. Everyone shorter than you move to this side. Everyone taller than you move to this side. That's kind of how this partition is going to work. So given this, which partitions do you think are valid here? We'll end on this note. How many people say A is a valid partition? Everything left of this 10 is smaller. Everything right of this 10 is larger. Yeah, that's true. Is B a partition? Yep. C? Yep. D? No, because it has a 4 there. All of these others are partitions, and using this, we can consider this as being more sorted than the previous. So overall, we're going to stop here. We're going to use this partitioning to create our full sorting algorithm starting next time. Until then, see ya. Friday, we are going to have a software engineering lecture. I believe this time it will be run by TA. So